record this computer and some annotation spotlight. Okay, so this is lecture number 19 of Physics 140. And okay, this is what we have been looking at before. We have been looking at the hydrogen. Remember, Ismail, stop me whenever, you know, we can talk about any subject here related to physics, I think. So the Schrödinger equation that we have been looking at is trying to solve this problem. We have a proton and sort of in the origin of the system, and we have an electron mass, an electron which is moving around, and we can sort of describe this thing as a function of this coordinates theta, phi, and r, and we somehow, you know, what I did was show you how people would do that, because it's a rather cumbersome and long derivation to actually solve a 3D problem with spherical coordinates in 3D. So what we obtain as finally as a solution, I actually asked you to look at this without looking at the blue lines yet. So forget about the blue lines here. So we find that the system actually has energy levels that are defined by the value of n, and the actual level here are minus 13.6 divided by n squared. So when n is equal to 1, we get 13.6 electron volts. Perfect. And then with n squared equal to 4, we get this minus 3.4 electron volts. And all of these things, let me, no, I don't have a nice diagram for that. But, you know, the energies are all negative because the electron is actually bound to the nucleus. So the energy would be 0 for an electron that can escape away from the proton. It will have enough kinetic energy to actually move away from the proton. So it will mean it could arrive to infinity, and it will not be bound to this particular proton here, okay? So the energies, the minimum energy that the electron can have is minus 13.6. And then we discover that there are another quantum numbers that are also interesting to consider, and those are the ones that are linked to the angular momentum of the electron. We recognize in this equation the solution of the hydrogen atom provides a way of recognizing the existence of the angular momentum in space, and the angular momentum, independent of the existence of a potential or not, is actually quantized. Okay, so you get this series of numbers that are actually possible for the L values. So the L values can go from 0 to n-1 for each of the energy levels. This is what is the right solution. That condition actually is found to be a right solution in such a way that the wave function is finite at infinity. Okay, we don't expect the electron to have an infinite probability of a finite probability of being at infinity. It should be around the position of the nucleus, and when we apply that boundary condition to the system, we find that the value of L's are confined to n-1 values. So let's see how does it work here. For example, in n equals 0, only the L equals 0 values are possible. Okay. So this L value was sort of labeled with the, you know, the label that was an S state. L equals 0 means S, L equal 1 means P, L equals 2 means D, and so on. Okay, and so we can use a way of labeling each of these states, which is the spectroscopic notation, which is here. Okay, and the spectroscopic notation is, this will be a 1s state. Why does it mean a 1s state in this particular, the state linked to this state here? Because it's the n equal 1. This is the first number, and then there is the orbital. The orbital is only indicating the angular momentum. This is done just to avoid writing a series of numbers that it should give a clue to what are the quantum numbers of the system. But essentially is that the first number is the n orbital, okay, is the shell, which also had letters here. So the K shell, L shell, M shell, and N shell. So K, L, M, and N are increasing letters, you know, that somehow reflect the value of N here. You know, this is K, L, M, N. Okay. Then goes P, ba, ba, ba. It keeps going on. Okay. And the states with in the second energy level here, we have also the possibility of having zero angular momentum, which is L equals 0, but also we can have, since L equal 1, since the maximum value of the angular momentum for the n equal 2 is n minus 1. N minus 1 is, in this case, is 2 minus 1. So the possibility of having L equals to 1 is also possible. And this is what we have here. I'm saying, I've told you before, forget about the blue lines. I didn't find this diagram without the blue lines. So that's why I have them here. I'm going to explain the blue lines in a sec. But you know, these are the possible values of n equals 2. You can have an S state and a P state. P state means a state with momentum angular momentum equals to 1. In the n equals 3 state, which is higher energy here, now you can have more angular momentum linked to this state, and this is, you can have angular momentum equal to 0, then you can have angular momentum equal to 1 and angular momentum equal to 2. Why only 2? Because it's 3 minus 1 is 2, and that's the boundary condition that we actually found out that was a reasonable one to get the right wave functions on this system. And this is, and you can actually fill this complete table here of quantum numbers. For the ground state, which is this state over here, you can only have n equals to 1, L equals to 0, and there's no component of the angular, or the C component of the angular momentum. You cannot have a C component of the angular momentum if the total angular momentum is 0. So you only have the 1s state here. Then you go to the second energy level. You can also have the 0, the L equals 0, the 2s state perfectly well here. And now we are in the L shell here. Before we were in the K shell. Now we are in the L shell of the because this notation here is not only valid for the hydrogen atom, it's also valid for many other atoms, and we will see how this come about. Okay. In the n equal 2 state here, we have the two possibilities of L equals 0 and 1. And the possibility of the quantum numbers of the C component of the angular momentum. Again, in the case of L equals 0, we don't have any component of the angular momentum, so ML is equal to 0. But when we have 1, the values of ML can go from minus L to plus L. So it will be L equals 1 goes from minus 1 to plus 1. So you have 3 values of the angular momentum possible. And you can see that there's always an odd number of values for the possibilities of the Z component of the angular momentum. It's 1, 3, 5, 7, and so on. Okay, you cannot have an even number, okay, of orbital angular momentum components along the Z-axis. Okay, so that's an interesting aspect of our solution. Then this is, you know, I'm reviewing this thing a bit because I may have gone a bit fast last time, or I don't know. Probably I just want to review it. And then we introduced the fact that we can place this whole atom in a magnetic field. And when the whole atom is in a magnetic field, the electron will be moving in a magnetic field. And you can somehow model the system as having if the electron is moving, it's kind of a coil in a magnetic field. Imagine in the Bohr model, for example, this guy will be moving like this, and you have a magnetic field in that direction. What will that do? Well, you know, we will try to align the magnetic moment of this rotating electron with the magnetic field, and that will mean that the plane of the orbit will somehow be tried to align with the normal to the plane of the orbit will try to be aligned with this B field that in general we assume to be applied along the Z direction, okay, for this expression over here, for example, okay. So when we do that, it means that there is an additional energy apart from the energy provided by the electrostatic interaction between these two elements. If I put a magnetic field, I have to add another energy term to my Hamiltonian, and in simple terms, is something like this. The actual orbits of the electrons are not modified, are only changed a bit in a way that they are given different energies. Okay, it's not that the actual wave function is changed substantially, because this is a very small energy difference. You have to realize that this energy here is of the order of millivolts compared to the energy of the electron and the nucleus, which is of the order of electron volts. These are order of electron volts, and the difference in energy here between the different magnetic fields, and this is what this graph means. Now we are applying a magnetic field, and the electron have a magnetic moment. The expression for the magnetic moment, do I have it here? No, I went on details over the last section, but it is placed here. It has to do with the momentum, with the angular momentum of the system, with the C component of the angular momentum. Where does the C component of the angular momentum comes in? ml times h bar is the C component of the angular momentum, and E over 2m is sort of the constant from that. You can scale the angular momentum to give you the magnetic moment of a system by this constant, E over 2m. Okay, so E over 2m is some sort of gyromagnetic thing, meaning if you multiply the magnetic moment by E over 2m, it gives you the magnetic moment of an orbital with a certain component of angular momentum. So if we take this whole number together and only retain the dimensions of the magnetic moment in this expression here, EH over 2m, this number here is what is called the Bohr magneton, okay? And this is a number like 5 times 10 to the minus 6 or something like that. That it's a very small number. I don't have it right now here, but I have it in the next view graph. Okay, so this is a very small number in a perturbing field. Here we have the magnetic field, and if we apply a magnetic field, anything that has a component of ml, then if it has a magnetic moment in the z direction of the aligned with the magnetic field, that thing will have different energies. So before the n equals 3, before I apply any magnetic moment, any magnetic field, all the states with n equals 3 will have the same energy. The ones with L equal to 0, the ones with L equal to 1, and with L equal to 2 will have the same energy, because the energy only depends in the solution of the Schrödinger equation on the value of n, okay? But if I apply a magnetic field, and I now know that there is an interaction because there is this magnetic moment associated with a rotating electron around a nucleus, I find there's a splitting, okay? And the magnitude of this splitting is relatively small compared to the electron volt scale. Actually, this value here is very big. It's just this distance between states here is very large. It has to do with this value here, isn't it? Because this is the difference between the ground state and the excited state, and the difference between the ground state 0 and the excited state is equal to this value, EHB divided by 2m. Okay. And that value, since EH divided by 2m is very small, B must be very large to actually be able to see this at this scale in the graph. Actually, I gave you a homework on this thing. So you should estimate the magnetic field in that people supposedly used in this diagram to actually draw it like that. So what is the magnetic field that could actually give you a diagram like this? And you'll find it's a huge magnetic field. I don't know how big it is, but I'm curious to find out myself. So that's why I gave you guys the homework, you know, to do the numbers. You know, you will have to measure things in this graph. If this is minus 13.6 and this is 0, you know the scale here of the energies. You can compare with this scale and see if they are scale, if this is minus 3.4, if they are consistent. And then you can measure, you know, the distance between these two guys by measuring the difference between that and that with minimal error using a ruler. Okay, that's my suggestion that you should do to actually find out what is the magnetic field here in this graph. We found out that there was a way of describing the wave function. The wave function gives you something reasonable in terms of probability distribution. Phi squared, the wave function, which is the solution to the Schrödinger equation, is not something that we can measure. We can only measure something related to the square of the wave function. The square of the wave function is the probability of finding an electron at a certain distance from the origin here. And here I have displayed several phi squared to different values of the wave function, the 1s, the 2s, and the 3s state. So a 3s state is n equals to 3 and L equal to 0. That's what an S state means. So this is sort of the wave function of that state, and you can you can actually see, for example, there's a very clear prediction of what the probability of finding the electron in the different positions is. Okay, so the highest probability is within this energy range here, this radius range. The scale of this graph is A, A is the Bohr radius here, because this is the natural distance in atomic units, okay? So the probability density, the phi square, is a meaningful result of this equation. And what I have just described you as you know, this phenomena of separation of states is called the Zeeman effect. And the Zeeman effect, you can, this is a case of a D state here. In case of a, now I'm looking at this expression again with a D state. So where D states, the M values, D state means L equal 2, and the M values can go from -2 to +2. And so this can go from -2 to +2. And this is the energy level of a D state when B is equal to 0. And when B increases, the separation between this, then this level here can separate in the different components of angular momenta here, okay? So this is the one where the B field is completely aligned. When the energy, when the angular momentum is aligned with the field, this is the highest energy. It has to be counter-aligned for the minimal energy, and the difference why the minimal energy is with the angular momentum in the inverse direction. If the B field is like that, the angular momentum should be like that, and it should be like that in order for the magnetic moment to be aligned with the field. Why is that difference in sign? Because the electrons have a negative electron charge, okay? So that's what the reverse mean. So the minus sign here is the minimal energy configuration. So this will be in thermodynamic equilibrium. This will be the state that will be filled with will most likely be occupied. If only I have one d electron, the one d electron will be most likely in this particular state, simply because this is the minimal energy for this particular atom. If for an orbital where I only have one d electron, okay. This I have not discussed really on details, but you know, here I'm going to sketch a bit what I'm doing here. Here I have a D level, the 3D level, which is you know, in the case, this is the 3, and the D level is the one that has momentum, angular momentum equals to 2, and I am considering electronic transition from this state to this state, okay? So this is the meaning of this graph. So I'm going from the 3D state to the 2P state in case that we have a magnetic field present on the system. So I'm applying a magnetic field. In general, this is something that I have not discussed before, but there are selection rules. A photon can only make transitions, I'm sorry, an electron can only make transitions emitting a photon if the difference in the M values is equal to 0 or plus or minus 1, okay? And the L value has to change in plus or minus 1 for that optical transition to be possible. What does it mean that's an optical transition to be possible? It means that a photon can make a transition from this state to that state, or I can have an electron in this state and it will make a transition to this state if emitting a photon, because it fulfills all these rules that the delta M is equal to 0, delta M plus or minus 1, and delta L plus or minus 1. How does that come about? Well, this is the D state and this is the P state. So they can always be transitioned between this state and this state, because that will mean that delta L is equal to 1, because this is, let me see, delta L is equal, no, delta L is equal to -1. Why is delta L equals to -1? But the L of the final state is 0, I'm sorry, is 1, and the L of the initial state is 2. How did I do that? Okay, I don't know what happened. So, so delta L is equal to -1 always between these energy levels and these energy levels. So whenever I have an optical transition between this and this rule for this pair of states will always be correct. So the one with the red arrow here. What we really have to verify is if delta M is equal to 0 or delta M is equal to plus or -1, you know, between these energy levels. Because you can have an electron being emitted when an electron makes a transition from this high-lying state to this state, because here you have an M equal to 2, and here you have an M equals to 1. So the delta M in this case will be just equal to -1. But if I make a transition and look at the dotted lines from a state here with M equals to 2 with an M equals to 0, that cannot be possible, because that will mean making a delta M equal to -2. And delta M equals to -2 is not possible, because the amplitude for a transition between this state and that state is very small. Okay, so it means that the only possible transition for a system in a D state in the highest angular momentum will be to the M equal 1 state in the 2p. Okay, these two things will be forbidden. You just have to account, and then you can look at all the arrows and possibilities here of making, and you can definitely see, if you have something like this, you can actually predict what are the most intense line, and it has to do with the number of arrows that you can actually draw. These are only one arrow, complete arrow. The dotted lines are forbidden ones. This has 2 arrows, so this is so if I plot the intensity of the transition as a function of the energy difference or the wavelength difference between here, the most intense line will be this one over here. So these guys, well, yeah, but for that one we have a singular population here. No. Okay, I'm taking this back a bit, because why I'm taking this back? Because look at this. The transition from this state here to all these states here have different energies. This has a different energy than this one, than this one, than that one. So one really has to find out what is how is the energy distributed here. You really have to not only measure the number of lines, but you should measure the difference in the Y scale, in the energy scale that we are seeing here. And there are coincidences. For example, this guy over here is 2 above, and this is 1 above, so it's this is +1, and this is here, and this is +1 too. So this guy and this guy, these 2 lines here have the same energy. So if they have the same energy, I could count them twice in the transitions falling down. This is complicated enough that I'm not going to give it as a homework, you know. But at least what I'm doing with you guys is actually figuring out the magnetic field that is actually providing for this energy difference. Okay. There's something that it's missing in our description, and what is really this missing in our description is the concept of the electron spin, and I'm going to try to explain to you how this was discovered. You know, they had this oven here where they produce neutral atoms, okay, that are that have one electron that actually gives the whole thing its magnetic properties, and this one electron, the magnetic properties that they should see is that what they expect to see is they should see no magnetic moment, meaning it was an atom with an L equals 0 state. It means that if I put something with an L equals 0 state in a magnetic field, the energy will not be changed in any way. But they did that experiment, they put a gradient here. If they have a beam of this particle and they have a gradient, something with L equals 0 should not feel any force, okay? But they actually saw that there was split in the actual beam. There was what one would expect here. If you see the beam coming out, I will see the same shape of this narrow slit drawn here. And this is in this glass plate detector that we have here, we can actually draw the shape of the beam hitting the glass plate here simply by looking most likely to the emission of light coming from the glass plate, okay? And they didn't see this, but they saw that there was a split in 2 levels of this beam of atoms that came out of here. So if this thing was an L equals 0 state for the outermost electron of this beam of atoms, I would expect to see a straight line here. Let's say it's not. We made a mistake. It should be an L equal 1. If we see an L equal 1, what we should see here in this position should be 3 beams to L equals -1, 0, and +1. But we didn't see that. This is not the result of the experiment. What they saw is that the actual, because as I'm telling you before, you can see this, we have a split, no split, which is L equal to 0. We see a 3-way split with L equal to 1, a 5-way split. So we only see uneven numbers of split in the magnetic moment, okay? And here we saw 2, the upper part and the lower part of the beam. So the guy started thinking, well, you know, there's something strange. There is some magnetic moment here, because there's some magnetic moment here that is probably due to some sort of spin, but it's a different spin because only have 2 components. You know, if something has 2 components and the magnitude of the magnetics, oh, I don't have the expression, and the magnitude of the magnetic moment of the modulus of the spin has to do with this thing, with L times L plus 1. So wow, it means if I have two components, it means that LZ must have 2 components. It means that ML must be fractional. So this is how they came up with an explanation that the electrons, a part of the orbital angular momentum they have around the nucleus, they have an intrinsic angular momentum that it has two components of the spin. That's why we call it spin up or spin down, which is it could have a spin which is equal to a half, plus or minus a half h bar. Okay, and this is what is consistent with the results of this experiment. Okay, there are, you know, the interesting thing is that you can actually design or think of a classical way of actually obtaining this. If you have a sphere of charge, a spherical distribution of charge, and you make that rotate at a high velocity, you can have that that sphere, since it's rotating, you can think of that sphere having well, it will have first of all an angular momentum, okay, and then it will have in addition a magnetic moment. So it will be, instead of an orbital magnetic moment, it will be an intrinsic magnetic moment coming out of a single rotation like that of the particle, okay? Because there's a charge distribution on it, and when the charge rotates around an axis, well, you're saying you have a current of sorts going around a certain position, and then what you would get is a magnetic moment. When people do the calculations and they compare with the experiments, they find out that they have to assume certain radius for the electron, you know, and nobody had measured a radius of the electron so far. So it actually needed a very high speed, and the speed was so high that the velocity of the extreme of the electron will be going faster than the speed of light, in order to produce results that will be able to compare to the experiment. So they decided, look, that is not a good explanation. The classical mechanics here, the classical electrodynamics doesn't work. So what we are going to assume as a theoretical model and see how far that can get us is that the electrons can move in an orbit and have an angular momentum due of being in an orbit with L equals 0, no angular momentum, L equals 1, you know, 3 components of angular momentum, L equals 2, 5 components. In addition to that, they could have an angular momentum that we will call spin, and it's an intrinsic angular momentum. Same as the planetary explanation of, you know, the Earth going around in the solar system. We have the angular momentum of the Earth around the sun is the angular momentum of the orbit, the complete orbit, you know, 365 days, you know, so many kilometers from the center of the sun. You can have an MRB, which is equal to the total angular momentum of the Earth. Plus, in addition, you have the intrinsic rotation of the Earth with respect to itself. Okay, so there's an additional physical angular momentum there, meaning you have, you know, and you can calculate that following quantum, following Newtonian mechanics from physics 110. Okay, but this is not what I'm telling you here. That is not a good assumption to actually do that, because that doesn't explain all the physical phenomena that has been observed, and the explanation work much better if you actually describe the angular momentum as an intrinsic quantity of the electron. And you will, if you have an electron here, it has an intrinsic angular momentum spin 1/2, and if you choose an axis, it will be, the spin will be going on that direction or on this direction. That's it. That's the quantum mechanic of a spinning particle. Okay. This intrinsic angular momentum will have the same shape as this angular momentum here, which is the orbital angular momentum in terms of how it relates to the units of h bar, with the difference that it is fractional. It's a half times a half plus one. That's a plus and a one over there, by the way, okay? So the c components of the angular momentum could be plus or minus a half h bar, the same way as this one are, in the case of L equal 1, for example, could be 1 h bar, 0 h bar, or minus 1 h bar. In the case of a particle with spin equal to 1/2, you cannot have a zero component of the spin. You know, you only have two components of spin. So the thing is always spinning, or spinning up or spinning down. You don't have the possibility of having zero intrinsic angular momentum. You know, the relation between the angular momentum and mu is in the case of the orbiting particle is minus EH over 2m. This is the Bohr magneton, multiplied by ml, which is the quantum number that actually defines the z component of the angular momentum. In the case of spin, we do the same thing. We multiply E times 2mc times the z component of the spin angular momentum, and we multiply that by g, which this is the difference between this, the orbital angular momentum, and the spin angular momentum in relation to the magnetic moment generated by something with spin c. And this value of g here is equal to this huge number here, which is essentially 2 for most of everything, you know. The number that I have written here is the prediction for this value when you do the proper theory of to calculate the gyromagnetic ratio of an electron, and it gives this value here. And this value here is one of the most precise numbers, and the theory that gives rise to this thing is called quantum electrodynamics. Well, quantum electrodynamics is the quantum mechanics of particles that can go very close to the speed of light. Okay, so where the fields are all there included, and you can see that this number is you know, a very precise number that could be used to and could be compared with measurements, because you know, if I could put this in a magnetic field and I could, you know, add some energy to, let's say you have an electron in an L equals 0 state, and all the magnetic moment is produced only by the spin. So you produce, you can change the state of a spin up and a spin down, and they will have different energies, okay? Depending on the alignment with respect to the magnetic field. So I put a magnetic field and the thing look, it also has the minus sign due to the electric charge here. Where is the H bar coming from? Because it should be an expression essentially like that. The H bar is contained in the SZ component. So the SZ component can be plus or minus H bar. So this is where I get the two components of the magnetic moment associated with spin. So again, the unit to measure magnetic moments in atomic level will be the Bohr magneton again, which is the Bohr magneton is EH divided by 2m. And did I write that down somewhere? I hope I did. No, I didn't. I wrote it last class. But it is a very small number that you will actually need to do your homework actually, okay? So this is the frame, this is the theoretical frame. People came, it took a while to actually figure this out, you know, and it is a good model to actually assume an intrinsic angular momentum for a particle. Essentially, it's a particle that have almost no radius, the electron. It's a point particle, but even though it's a point particle, it has an intrinsic angular momentum to it. So it will collide with something, it will have some angular momentum. The same way as the photon has an angular momentum, the photon has an angular momentum of 1, and that's why the transitions between a state, you know, the electronic state up and electronic state down, the delta L should be equal plus or minus 1. Plus or minus 1 has to do with the photon carrying away the energy from a transition from an up state to a down state. It's carrying away also some angular momentum, and the angular momentum is carries it's L equal 1 associated to the particle. Okay, so this is a reason for the rule of conservation of angular momentum in transitions, in optical transitions where a photon is emitted. Okay. And so this is the relation between we can somehow define a magnetic moment for a particle only with spin in this way. So it means that if we put this in a magnetic field, we will have a difference in energy. Okay. So the magnetic moment associated to a particle with spin will be plus or minus EH over 2m, and this is the Bohr magneton again. Okay, so that would be the difference, the Bohr magneton. If I put a magnetic field on it, you know, and there's only mu, this mu here is only related to the spin magnetic moment, I could get a change in the energy of this state by applying a magnetic field. Okay. So even if we have a state with L equals 0, I will have a splitting of an L equals 0 state due to the presence of a magnetic field, because now I have to consider the intrinsic magnetic moment of the electron, which is linked to the intrinsic angular momentum, which is the spin. Okay. Now, let's consider this concept, which is the spin-orbit coupling. If we look at even in the case of hydrogen atom, or in particular in the case of a hydrogen atom, if we somehow put a magnetic a frame of reference in the electron, what we will see if we actually stand in the electron. If we stand in the electron, we will see the proton going by around. You know, it's like us on Earth. What do we see with respect to the sun? We see the sun that is making a circle around us. You know, it's circling. That's what we thought from the very beginning. You know, that the sun was circling around the Earth. You know, but that is not what happens. We are circling around the sun. We know that now, and the Earth is not flat. You know, by the way. Yeah. So this is the way we can see this, and if we see this, well, this is charged positively. So it looks like in a Bohr type model, this will be rotating around the electron, and it will be some sort of a loop current going around the electron. A loop current going around the electron, apart from the electromagnetic field felt by the electric field, there will be a magnetic field by the fact that the two things are actually moving. Okay. So if the thing is the electron is the proton it's since the electron is moving around the proton is moving around the electron, and it actually generates a magnetic field in the position of the electron. But the electron has an intrinsic magnetic moment. So the intrinsic magnetic moment of the electron will interact with the orbital magnetic moment of the electron itself, because the actual trajectory of the proton around the electron is actually proportional to the magnetic moment of the electron. Okay, so I will have the field that the electron will feel in this point will be proportional to its own angular momentum. Okay, so this is what I write here. So it is almost as a loop of current that generates a magnetic field proportional to the orbital angular momentum of the electron. Hence, the spin, the spin of the electron will see, we'll see an effective magnetic field, which is a function of R times L. And this function of L, it will really depends on the orbit of which angular momentum I'm considering. The effective magnetic field produced by an L equals 3 will be different than an L equals 4, because the distance to the nucleus is different. So the size of the equivalent coil or circuit that the proton will follow is different. Okay, so but let's not get into those details. I'm just going to say that the effective angular momentum is a function of R, probably evaluated, and this function is a function of R and L. To be fair, I should put L here too. Okay, but this function of R, it's a scalar function. It's not a vector, and it should be evaluated at the Bohr radius. Okay, so essentially the energy of the states will be changed now because of the interaction of the intrinsic magnetic moment and this magnetic field that is produced by the rotating proton. Okay, so the effective magnetic field will have the effective energy will have a form like this. Okay, we'll have this here is the magnetic moment of the GEMS is the magnetic moment of the electron, the intrinsic magnetic moment, and the FRL will be the effective magnetic field, and the interaction of the two will generate a split on energy. But that effective magnetic field is not even present, meaning it's coming due to the motion. So I don't have to apply it externally. So naturally, if I include this effect of the interaction of the angular momentum with the intrinsic magnetic moment of the electron, I will get a splitting of the energies. Okay, so what I thought at the beginning, there was no effect when I solved the Schrödinger equation. I didn't include the spin of the electron in any way inside. I didn't get the effect. But now that I know that the effect exists, I have to modify again the Schrödinger equation to actually include this effect. Okay, and this is what people have done here, and I have an example here. And how much time do I have? I have 10 minutes for that example. Okay, so it's the yellow light in the sodium lamps. If you look to Valparaiso at night, Viña del Mar, you see that it looks yellow. Most of the lights that were installed there, I don't know if they're still there. Probably they're still. The yellow lights are coming from sodium. So it's the excitation of a sodium transition. What sodium transition is a transition of electron from an excited 3p state to an 3s ground state. Okay, we will see this in further detail at the end, but what we should know now is that this 3p state, because in the 3p state you have an electron in this state that has an angular momentum, there's an interaction between the orbit and the spin. The spin-orbit interaction here produce a splitting of the state. Instead of being just a 3p state with a certain level, you get a separation between the two levels because of the spin-orbit interaction. So the question is, estimate the value of the effective B seen by the electron in the 3p state. Okay? If something here, I don't know what it is. But I found this very nice set of transparency that I'm going to share with you. This is the way, this is the actual origin of this thing. And so to give proper credit to the people that did it, I didn't do this. So this is actually a spectra of a sodium lamp. And this thing here is energy in this axis. And these the vertical axis outside the page is intensity, and they are showing here, you know, this is the way it looks. It looks sort of very narrow, and then you get these two very narrow lines here. Okay, so the sodium spectra is dominated by two bright known sodium D lines. Okay, D. So what does the D means? I don't know what D means, but it is the transition from the 3p level to the 3s level. D, it could be doublet actually, because since there are two lines, they call it a doublet. And the energy of this line is that value. The difference is very small. And so you can actually estimate the splitting between the two and actually calculate the magnetic moment. I'm sorry, the magnetic field that will be required if I actually put it from the outside to actually generate this sort of splitting. This sort of splitting is very small, actually. See, this is 88.9 and this is 89.5. So it is, you know, and these are nanometers, by the way. Yeah, nanometer, that's the unit here. Okay, so that's the way it looks. This is the way the energy diagrams could be understood. We have a ground state, which is a 3s state. A 3s state, it has only angular momentum a half. This is the angular momentum of the system. The total angular momentum is a half. What does it mean, a half? It means that you know, you have to add the orbital angular momentum and the spin angular momentum to get the total angular momentum. But in an S state, it's an L equals 0 state, so you don't add anything from the orbital part. The total angular momentum is equal to the angular momentum, the intrinsic angular momentum of the system is equal to the spin. So this is so there's no spin orbit interaction in the 3s state because S is equal to the L part of the angular momentum that could have some influence. This part here is 0 for the 3s state. But when I have an M state here, I have, you know, there's something that is different. When I have an L equal 1 state, a P state, this value is different from 0, okay? And so this is what happened here. So I have a splitting of L with S, and the value of the splitting is 0.0021 electron volt, which is a very tiny bit, okay? So this is the difference between the two energies that split by spin-orbit interaction, okay? And the question is, what is the type of magnetic field you actually need to produce that splitting? This is something, well, you can go through this in the later. Let me get to my notes here. This is the same schematic of the transition. I don't know if these values are actually the same. I think they are the same. Okay. So the difference between these two levels up here produce a difference which is equal to 0.0021 electron volts. And I have to divide this thing. This is the number of 5.8 times 10 to the minus 5. This is the Bohr magneton. I actually wrote it in this note. Okay. So in order to get this, the value of the equivalent value of V, I have to divide the difference in energy by twice the Bohr magneton. I know this is not a value of magnetic field, of applied magnetic field. This is the magnetic field that the electron in the 3p state feels because the nucleus is actually rotating around. Okay, so this is what is called the spin-orbit coupling. Okay, perfect. So we have a number for that. There are interesting way of actually labeling the states. I actually did this a brief note here. So we have the total angular momentum. We call it J. J is equal to L plus S. If I have a particle with an angular momentum equal to 1, the total J can be, there are two possibilities, or the spins align up if I have an intrinsic angular momentum, or they are anti-aligned. So if they are aligned up, the total J should add half a unit of angular momentum, h bar over 2, or can subtract h bar over 2 with respect to the orbital angular momentum to get the total angular momentum. So let's say I have an orbit with L equal 1. With L equal 1, I have two possibilities of total J. The total J could be 3/2 h bar, or it could be 1/2 h bar. So it's 3/2 or 1/2. Okay. So and that's the way they are labeled here. So we have a state with total angular momentum equals to 1/2, or total angular momentum equals to 3/2. The P is a label for the orbital angular momentum. This is J, the subindex here, and this here is equal to the possibilities, the multiplicity of the spin particle, meaning you can have a total spin equal to 2. I'm sorry, if you have spin equal 1/2, you have two possibilities for the spin, up or down. So this value that goes here is 2s plus 1. And 2s plus 1 means the total number of components that you could have of the angular momentum, okay, of this spin part. The J part, you could have, 2s plus 1 here. So it's 4 components for the 3/2, okay? Let me see if I'm, I don't want to deal with that. There's enough information, but there's something interesting here. This is what I showed you before at one point. This is a solar spectrum showing absorption lines. And we are seeing the things that are coming from the sun, and then we see a line that is missing here. because if a line is missing, that line is being absorbed somewhere. And if we look at sodium, we find out that the position of the sodium is exactly the line that is missing there, okay? So if that's the case, this means here that there's sodium in the atmosphere of the sun, okay? And which is actually absorbing light that doesn't come here and absorbs exactly here. And this light here is a doublet. What doublet is this doublet, okay? You only see it very narrow. You see it as one single transition because of that, because we don't have enough resolution to see it here. So, but actually it should look like that. That's the doublet that we should be seeing. And this is interferometric emission. This is in wavelength. So let me see. No, this is not, there's something strange with the scale. I have to see what does this mean. I only put it in when I saw it. Well, the thing is, when you see a city from above and you're seeing the yellow lights of the lights that are illuminating the city, you should know that that light over there is a doublet, okay? So that you know that's the way they look. They look this funny looking thing that you look almost green when you're actually illuminated by this yellow light at night, okay? So the key aspect here is that the interaction between the orbital angular momentum and the intrinsic angular momentum or magnetic moment of the electron that produces this splitting in atoms that is called the spin orbit splitting. And that thing is actually the subject of the lecture today. And this is what we call the fine structure of the hydrogen atom. And probably, you know, I've already told you about this, but let me stop the lecture here and try to recover it from this view graph next time. We don't have much, but there's a homework here, and I would like you to work out the details. Yeah, in the view graph 2 of this lecture, estimate the magnitude of the B field that gives rise to the splitting of energy levels. So you have to see, you know, measure with a ruler essentially and estimate what would be the field you need to actually produce that image in splitting.
All right.
Okay. Only assume that S is equal to 0 on that. Only this orbital spin is what counts for that image, because we didn't introduce spin at that point. Okay.
Okay.
And then read somewhere, internet if you want, and write a sentence or a paragraph, 5 or 10 lines, explaining what is the hyperfine structure of the hydrogen atom, okay? And what is the relevance of its application in astronomy. I should write hyperfine structure of H, okay? What we have just described here is the one that, this here is the fine structure, the one that is due to the splitting of the levels due to the L.S interaction. But there's something that involves the nucleus. And you have to explain to me in a few sentences, read about it, it's direct. It's the same thing that I've been telling you. So
all right, perfect.
Okay. So this is the class for today, guys. See you on Thursday.
It'll be Thursday, yeah. Take care, teacher. I hope you have a great day.
Okay, ciao, ciao.